Okay. Hello, everyone. My name is Ajay Jacob. I am the Director of Projects at the California Dreams Hub. It's my pleasure to invite Dr. Basim Tasson. He's a principal research scientist at Hewlett-Packard Labs. He focuses on optical computing technology from diverse optoelectronic materials and devices to large-scale programmable photonic integrated circuits and architectures. The theme of his research include the heterogeneous integration of various dissimilar materials on an integrated photonic platform to leverage the strengths of different materials and enhance both energy efficiency and scalability. The development and characterization of novel photonic non-volatile memory materials and devices for in-memory optical computing, and the co-integration of emerging electronic and photonic devices to create new capabilities in storing, processing, and communication information. He will give us a talk on lighting up the frontiers of computing. So once again, it's my pleasure to invite Dr. Basim. Basim, the floor is yours.
Sounds good. Thank you very much for the introduction, AJ. Yeah, my name is Basim. I'm a principal research scientist at Hewlett-Packard Labs, and as AJ mentioned, I'm going to speak a little bit about some of the work we've been doing in optical computing as well as optical networks interconnects for next generation AI hardware. And so just to begin, give you a little bit of introduction of Hewlett-Packard Labs. So HP was actually the birth of Silicon Valley. The garage, as they call that, is the actual birthplace, and you can actually now I don't think it's open to the public, but it's actually still there and around in Palo Alto. And in 1966, Hewlett-Packard Labs was then founded, and to basically work hand in hand with the businesses to guide and direct the business units towards next generation products. And so I work part of a team called the Large Scale Integrated Photonics team, and we span across a few different locations around the globe, actually. So we have a team based in the Bay Area as well as a team in Santa Barbara, which where I'm located. Then we also have a team based in Brussels, Belgium, and we've uh, have several years of experience in the field of silicon photonics and integrated photonics. And we also compete for research grants and perform fundamental research as well as applied and advanced research. And we try to connect closely with the business units to kind of, again, as I mentioned earlier, guide them onto what are some of the next generation technologies to invest in, as well as to try to pursue tech transfer of some of our own in-house Hewlett-Packard Labs technology directly within the business units at Hewlett-Packard Enterprise. Let me just put my pointer on. So, as you may know, Hewlett-Packard Enterprise, we build supercomputers and data centers, and actually, the world's fastest supercomputer is an HPE system, and it's in the top 500. We actually, I think, have three of the top five supercomputers in terms of speed as well as energy efficiency. And I think a few years ago, we reached an exascale. And it's these exact systems, these supercomputing systems and data centers that are the backbone of modern AI. And actually, a couple of years ago, the Nobel Prize winners, Geoffrey Hinton and John Hopfield, they were working on artificial neural networks. And Geoffrey Hinton, who's the father of deep neural networks, he made the claim that the deciding factor for the AI revolution was the increase in compute power. And I think a lot of the credit for deep learning goes to the people who made the computers go fast. So it's exactly that increase in compute power that we have available today, as well as the amount of data, vast amount of data we have available as well, that allows us to build these large-scale AI models and neural networks that can run those systems. And the current issue that we're seeing, though, as we build these systems and we scale them up, we scale up and scale out. we see an issue called the memory wall, where actually the amount of memory provided in these systems um, scale with Moore's law every 2 years. However, the transformer size or the model size and the number of parameters scales at a much faster rate. In fact, the computing power demands because of those models is increasing at a rate such as every 2 months it doubles. And so with that, there's a large gap in terms of performance and what was actually needed for computing performance. And then a much larger demand that is also then required on compute power and energy consumption. In fact, when you take a look at the carbon footprint of training a current large language model, it's actually 5 times that of a car lifetime or consumption in its lifetime. So this is becoming problematic and actually increasing at an alarming rate. So we need to perhaps think a little bit going forward of how to build these computers. So, this is a nice little timeline of uh, the evolution of computers over the years. We began with these sort of steam engine or steam powered type of computing engines or computers, and then we had electromechanical based ones such as the Turing machine. Alan Turing worked on for the Enigma project in World War II. HP also got involved in the computing business, and then the von Neumann architecture, which is now the most widely used architecture and used in pretty much every computing system, is currently running on systems. And back then, von Neumann also worked on variations of the world's first supercomputer called the ENIAC, which is then at that point was all electronic. And then Cray built the first megaflop or mega scale supercomputer, and then HPE, as mentioned earlier, has built the world's first exaflop or exascale supercomputer. So going forward, what's next? Are there different kinds of technologies we should be looking into to continue this pace, but also doing it in a way that is still energy efficient? So when we compare the HPE Frontier supercomputer to the world's most efficient computer that we know, which is the human brain, there's actually a huge difference in the power consumption. Um, Human brain consumes just about 10 or 20 watts of power to process about an exaflop of data or information, whereas a frontier supercomputer consumes about 6 orders of magnitude more energy to do the same thing. So there's an obvious difference, and we need to perhaps be inspired and learn a little bit from the human brain going forward. Uh, why is it that it's so efficient, and how is it so efficient? Can we build computing systems that also can be this efficient? One of the main reasons is that the human brain has such a massively dense web of interconnected neurons. In fact, something around 10 to the 11th number of neurons. And it's not that this information is actually, or the signals that are being propagated in these neurons are that high speed in comparison to what we use today in electronics. They're actually around a kilohertz in bandwidth, but it's just the fact that you have so many of these neurons massively parallel processing that allows you to achieve this level of information processing at such energy efficiency. So people then became brain inspired by the brain to build neuromorphic computing systems. So John von Neumann actually wrote a book called The Computer and the Brain, and some of the very first models of the computer were actually based on the human brain. And when you look at biological neurons and neural networks, we can learn from them and model basically the way that these neurons communicate with each other. They have synapses where neurons are either strongly connected or more weakly connected to each other by the strength of that synaptic weight, as we call it. And so that's something that can then be modeled also by an artificial neuron. And actually, in 43, McCulloch and Pitts put together the first perceptron or artificial neuron model, which consists of inputs to a specific neuron that are multiplied by weight values, and then the summed or the weighted values are summed up. And depending on that summed value, it will then output either say a one or a zero or a spiking signal, basically some sort of output response based on an activation function. And this really is just comes down to a couple of fundamental linear algebraic operations and a nonlinear operation. So it's a multiply, it's a summation, and then it's a nonlinear operation that is run on that weighted sum. So from these artificial neurons, you can then build these larger neural networks where these neurons are connected together, and then you can train these neural networks and teach them to actually begin to understand patterns and data sets. And then after they've been trained, you can then infer. And so inference can then basically take new data and try to detect patterns and draw conclusions from that data using the trained model. And so these neural networks have many, many layers. They're interconnected with all of these different synaptic weights. And in order to train these neural networks, you need to run something called backprop. One way to do this is with a method called backpropagation, where the weights are optimized from the output being fed backwards, layer by layer. Those weights are optimized to then make sure that the outputs have as little error as possible. Um, and the key mathematical operation for these neural networks is a matrix vector multiplication. So looking at the current accelerator hardware landscape for AI, as we mentioned, the human brain is actually the most efficient computing system. But when we look at how we're running these matrix vector multiplications for neural networks, with our current computing systems is actually quite inefficient. And the main reason for that being the von Neumann bottleneck. Each time you run a matrix vector multiplication operation, data needs to be moved between your processor and your memory, as well as your nonlinear units. And every time that occurs, power is consumed. Another reason that this is limited in its performance is the bandwidth. So the amount of data that can be shuttled from the processor to the memory and back is also limited, which is also coined as the von Neumann bottleneck. And so you have both limitations in terms of bandwidth and as well as efficiency. And so people have started then looking at parallel processing through processor units such as GPUs and TPUs, where you have many of these cores processing matrix vector multiplications in parallel. But then once again, as you do that, and you have many, many cores processing in parallel, again, the amount of data movement increases, and most of the energy lost actually becomes or comes from that data movement. So how can we break past these walls in both efficiency and speed and get into this gray region here? This is where integrated photonics can potentially become useful. So matrix vector multiplications can actually be done in a single clock cycle at the speed of light. So very, very low latency processing can be done with these integrated photonic processors. Data movement can be done without impedance effects. So that can be done, data movement can be done very efficiently. And this is one of the main reasons we use optics for interconnects in HPC systems. The data can be encoded at high frequency. You can leverage the high bandwidth properties of these optoelectronic devices. And another key advantage is that you can leverage different modalities of light and process data in parallel over all of these different modalities. For example, you can use wavelength division multiplexing, polarization, spatial multiplexing. All of these different modalities or dimensions of light can be processed over, which can then increase the throughput of your system as well. And then the fact that today we have markets driving silicon photonics and integrated photonics, we can leverage those current foundries and manufacturing processes that are available to be able to build these systems and scale. And so how can we get even closer then to what the human brain can accomplish is we could build integrated photonic systems that are inspired by the brain or neuromorphic photonic processors. So the current state of the art, there have been various demonstrations of photonic neuromorphic computing hardware from a number of different research groups as well as some startup companies. And it's quite an active and hot research topic. And there's a lot of significant advancements being made, and it's quite promising. But there are also a few key challenges that need to be addressed before this can really make a larger impact in a market. The first challenge is a lack of an energy efficient device platform, which can monolithically integrate all of the devices needed to build photonic neural networks or neuromorphic computing systems on the same platform or same chip. For example, the light emitters and amplifiers on silicon photonic systems tend to be a lot of times external to the chip, but bringing them on the chip will make it so that these systems can actually integrate, lasers, amplifiers, as well as other types of devices all together on the same platform. Second challenge is a lack of efficient photonic memory. So there's still a bottleneck in the optoelectronic conversions that occur. Each time a photonic core performs matrix vector multiplications, it still needs to go to external memory to be able to get the weights, the weight values. It also needs to be converted from the analog to the digital domain. And so every time that this occurs, you're consuming power and also adding latency to the system. So being able to do in-memory type of computing where you have photonic memory that can actually store data, that can actually help the inference and the training of these photonic neural networks to be a lot more efficient and mitigate that bottleneck by going to external memory. And then the third challenge is scalability. So these integrated photonic accelerators, they have challenges when trying to achieve larger scale circuits. And the main reasons for those being the optical losses coming from the devices and the waveguides on a photonic circuit, and then also the footprints of these devices lead to large circuit footprints. So I'll talk a little bit about how we've thought of addressing some of these challenges at HPE Labs. So the first challenge is this lack of an energy efficient monolithic device platform. So currently silicon photonics systems are mostly or most commonly used to build these neuromorphic photonic circuits. However, those prototypes are limited by the waveguide losses. Again, each device has its own insertion loss, and as you need to scale the size of the system, these numbers start to cascade and start to become very difficult to manage. Also, many different variations of prototypes use thermo-optic phase shifters to do your phase shifting and guiding the modes to your circuit. And that consumes milliwatts of power consumption, as well as adds thermal crosstalk within the circuit, which adds complexity in terms of controlling and in terms of the way that you would need to process the circuit or you need to design. And then most prototypes also do linear processing, so they can do matrix vector multiplication, but it's difficult to achieve nonlinear processing unless you're using some sort of exotic nonlinear optical material. It's difficult to do that. And also there's no on-chip gain. So needing lasers and amplifiers will have to be off the chip. And so that introduces additional coupling losses. And then also high-speed modulators lead to also existing or excess loss, I mean. So how can we address some of these things? Well, adding 3.5 directly on the chip can actually address a lot of these issues. So silicon is an indirect bandgap material, and so it's not known to be good at producing efficient light emitting devices. And so using a direct bandgap material such as 3.5 compound semiconductors can help you achieve that. And so what can be done is to actually then heterogeneously integrate these 3.5 compound semiconductor materials directly onto a silicon photonic platform, then you can then process and develop lasers, amplifiers, as well as other types of devices, including photodetectors and high-speed modulators, uh, all in the same platform. So it gives you low loss, high speed modulation. It also gives you the ability to do fast, low power, non-volatile photonic memory, which I'll speak about as well. And then you can also do the not just the linear processing, but the nonlinear processing of the optical signals as well. So to address this challenge, we've actually used this platform, this 3.5 on silicon platform, um, to provide all the devices needed to develop a neural network or to compose all the devices together to build a neural network all in the same chip. So, for example, you have your inputs. These inputs can then be provided by comb lasers, which provide multiple wavelengths, which represent multiple inputs. For example, the weights could be represented either by volatile or non-volatile phase shifters. And ways of doing this are again using high-speed modulators, or in our cases, we use memristive type of devices for non-volatile memory to do in-memory computing. Again, I'll go into that as we go in later into the presentation. And then you can also do your nonlinear activation function using different types of um, optical devices with nonlinear properties, such as lasers and detectors. So over the years, we developed a very nice device library of lasers. Quantum well and quantum dot based lasers have been developed as well as single wavelength and multi-wavelength lasers. And initially, we were using these lasers for CWDM, DWDM optical links, but they can also then be used for optical computing as well. And we've seen that we can get continuous wave operation over 100 degrees. And we've even designed some novel MOS-based laser structures, which allow you to tune the wavelength of your laser with very low power as well. So I'll go a little bit into that. And then avalanche photodetectors also have been developed, both on silicon germanium as well as 3.5 based APDs. And silicon germanium can give you the type of scalability and yield you need. It's a mature technology, and we can integrate it directly within our platform. And then 3.5 quantum dot based APDs can also be an option to get you nice, simple fabrication. So you're leveraging the same epitaxial layers and process that you use for your lasers. And then the fact that they're quantum dot based photodetectors, they can actually get you much lower noise and lower dark current in your photodetector. And that's something we also had demonstrated. And for photonic neurons, people have looked at different variations of building photonic neurons. And so these nonlinear activation functions can either be what we call optoelectronic or all optical. So in the case that they're optoelectronic, you have conversion of data from the optical domain to electronic domain and then back to the optical domain. And there's a couple of ways of doing that. One could be by using lasers or modulators, and these can be quite robust and well developed. For example, if you have a photodetector that detects your signals and then it directly derives laser by injecting current into a laser, that's a system that tends to work pretty well. But by doing the optoelectronic conversion and going from the optical to electronic domain, then you're consuming power every time you convert the data and also adding a little bit of latency too. So there's also approaches of doing this all optically, where you can then pump, say, a different type of nonlinear material, phase change material, or some sort of optical gain material like a laser or an amplifier to then give you a nonlinear activation type of function. And so this saves the energy needed or used in optoelectronic conversions and can be actually inherently faster than them as well. So we demonstrated a couple varieties of these nonlinear activation functions on a photonic platform. So the first is using all optical injection locked lasers, where we actually input light directly into a laser at a specific wavelength, and we see some nonlinear properties basically in the device that allows you to um, get a sigmoid type of activation function at the output of the laser. And this is due to some four-wave mixing type of processes with going and mode competition within these lasers. And then we've also been able to build in non-volatile memory into these lasers as well, so that we can um, also have optical memory directly or memory stored directly within the laser. And then in terms of optoelectronic neurons, we've looked at using APDs and lasers directly integrated on the same chip. And these APDs drive these lasers directly with the photocurrent that's generated. And we see that we can build ReLU type of activation functions from those devices. So I'm going to now shift gears a little bit to a different type of neural network. So they say that there are three generations of neural networks. First generation are those based on the McCulloch and Pitts neurons that I've talked about earlier. Second generation are these artificial neurons that can have other types of activation functions over a continuous value range from 0 to 1, such as sigmoid or ReLU or leaky ReLU. And then in the third generation, spiking neurons are employed, which basically codes information not just in the amplitude of the signal, but also in the time domain. And so it gives you another dimension to code information, but also it can be quite robust to noise, and it has other inherent advantages as well. So the way spiking neuron works is you apply a specific current to a neuron. For example, in this case, if you look at a neuron, if you apply a current across of the axon between neurons, you'll see that after you've pumped it with enough current, you'll actually see a spike released from that neuron. So this is actually most accurate to how biological neural networks actually work. And so the spike signals then are used to represent data. And depending on the rate of the information of the frequency of spikes or the time of arrival, there are different ways of actually coding information. So here you might have a neuron that has input spikes arriving at different frequencies and different time intervals. And again, depending on if you're using something called rate coding, you can code information by the frequency of the spiking signals. Latency coding can then be used to represent information by the time of arrival of spikes. And then there are other also types of modulation, such as basically positive or negative spikes or excitatory, inhibitory spikes. And so we've thought of actually then building spiking neurons from lasers, 3.5 on silicon photonic lasers. And an ideal excitable or spiking laser neuron should offer a minimal footprint, a reduced power consumption, and it should be scalable. You should be able to cascade these neurons together. So that's important when it comes to building a large-scale system. And so we've looked at using our quantum dot microring lasers to precisely achieve that. So what's nice about these microring lasers is that they are inherently compact. They have very low threshold current. In our case, we've seen in the single to few milliamp range, and they can be potentially lower as well. And then they can also, as I mentioned, be used for high-speed spiking lasers. So we've seen that they can achieve spike rates that are 10 to the 6 times faster than the human brain signal processing. So this is some recent experiments that we've run where we can actually inject light as well as current into this microring laser and control the type of, well, first get output spikes and then you can control the rate and the amplitude of those spikes depending on those input conditions. So they can be used to represent a what we call a class one excitable spiking neuron. And another way of doing this is simply by directly modulating these lasers. And we've shown that we can actually modulate these lasers with pulse widths as short as 62 picoseconds. And in either case, whether you're using optical injection or whether you're using directly modulated lasers, you can actually achieve about 10 femtojoules per spike. So this can be used towards building very low power spiking neuromorphic processors. These are much lower power consumption than CMOS-based systems such as Intel Luihi chip. And the spike rates can then also be much faster than what CMOS chips can provide as well. So this is kind of the direction we're looking into in terms of building very low energy neuromorphic processors for applications such as image processing and edge processing. So going back to some of the key challenges, the memory access for these photonic neuromorphic accelerators. Every time you
Bassam, we lost you for a minute there, for a couple of seconds. So if you could repeat, that'd be great.
Sure. Yeah, I was just saying that there is an existing memory bottleneck in these neuromorphic photonic systems. So again, every time data needs to be processor and your external memory, you have to convert data between optical to electronic domain, and DACs and ADCs are involved. And that actually ends up being some of the main power consumers within the system. So when we've actually did energy consumption analysis of these photonic neuromorphic accelerators, and we're seeing that actually a lot of the power, most of the power is actually consumed in that process, and only about 10% of the overall power is actually consumed by the photonic circuit. So it's really the peripheral electronics that uh, consume a lot of or the main consumption of the power. So one solution to that is to do in-memory optical computing. So by computing in memory, you don't need to then go to external memory to retrieve your weight values. So this can dramatically reduce the energy consumption of the system. And there have been different approaches people have looked at for doing in-memory optical computing. There have been also different materials and non-volatile memory devices used, and that I'll discuss. But really, there's a really important need for a very efficient photonic memory. And so inference of these optical neural networks currently consumes high static power consumption from the devices used to represent these weights. And then training also requires that these weights are updated frequently and with high speed. And so we need a high speed, low power, and compact photonic memory for these photonic neural networks. And so the current prototypes used a variety of devices. One of the most common ones is a thermo-optic phase shifter, but those tend to consume quite a bit of power, especially as you need to scale the size of your network. And they also can be slow in their switching speed. People have also looked into different non-volatile memory, such as phase change memory or phase change materials, also ferroelectric type of memories based on barium titanate. And then we've also looked at things such as charge trapping or flash memory and memristor based memory. But all of these different devices have their trade-offs. Some can be quite efficient, but maybe slow in switching speed, or maybe some can be faster in switching speed, but consume too much power or footprint, or they can be limited in their cycling or endurance. So at HPE Labs, we actually have a history of building MOS type of devices, which are actually used within the MOSFETs, of course. And one of the co-founders actually of HP Labs was one of the inventors. of the MOSFET. And we also developed the first memristor in 2008 based on titanium dioxide. And then later on, we also developed the first heterogeneous MOS cap. So we were able to build these MOS capacitors within a silicon photonic 3.5 on silicon photonic platform, to be more exact. And from that, we were then able to build very low energy MOS cap modulators, lasers, and memristive photonic devices as well. And so these MOS cap structures, um, basically they accumulate carriers on the 3.5 as well as the silicon regions. And those carriers that are accumulated within the waveguide of the optical waveguide create a plasma dispersion effect. And then that then creates a corresponding refractive index change. And so we can actually use these devices to act as phase shifters and as modulators and do this with very little power consumption. In fact, we say it's near zero power consumption. It's actually within nanowatts of power consumption, which can be several orders of magnitude less power than a thermo-optic phase shifter. And what's nice is that they can be conveniently integrated to our other heterogeneous photonic devices on silicon photonic platform. They're athermal, so they don't actually dissipate much heat. So the thermal crosstalk becomes less significant of an issue. And then you can actually make these circuits more compact and denser. And then they can also be used for locking to specific resonant wavelengths. So basically for DC tuning, if you're looking at, say, a DWDM type of optical link, instead of using a thermo-optic phase shifter to make sure that the rings are tuned to the correct resonance or resonant wavelength, you can use these MOS capacitors for that same reason. They can also then be used for high-speed modulation, and that's something that we've shown. We've shown we can get up to 25 gigabits per second modulation with these devices, and with pre-emphasis up to 28 gigabits per second. And then the next evolution of that device was then to demonstrate non-volatile memory within the same structure. So what we've seen is that if you apply a high enough electric field across of that MOS capacitor structure, you actually can create a conductive filament, and that forms from oxygen vacancies within your oxide material. And then you can then reset the device and rupture that filament. And by doing this process, you can actually change the resistance of the device, just like a resistive RAM type of device. And when you change the resistance of the device, you also get a corresponding change in your optical refractive index and then also phase shifting. And so we've demonstrated these memristive devices directly within microring resonators as well as Mach-Zehnder interferometers. And we've shown that we can get retention times as long as 24 hours. And we have the record switching speed and switching energy of any non-volatile or any type of phase shifter on a silicon photonic platform using those devices. And so if you envision a photonic neuromorphic chip that uses these devices, we can imagine that you can build a chip with lasers as well as these non-volatile memory structures and volatile memory structures and devices all in the same circuit. And you could then do both inference and training of these neural networks at very low energy and high speed. So one of the most common types of neural network architectures in photonics is the MZI mesh. And so here, basically, you can use these optical switches, MZIs, and by controlling the phase shift in the MZI, you can then also guide the modes and create constructive and destructive interference, allowing you to then represent matrix vector multiplications. And so Light Matter is a company that had demonstrated some of these MZI meshes for photonic neural networks, and very impressive and promising technology. Though just as a technology when you need to scale these MZI meshes to become larger than uh, what the current scaling is, which is around 64 by 64 meshes. You start to run into issues such as footprint becoming too large, and then the insertion losses and waveguide losses also start to become really large as well. And so you can see that scaling these photonic circuits is really challenging. And so the way that we've thought of addressing that is to use a method called tensor train decomposition, which basically allows you to take a weight matrix that is sparse and be able to compress that weight matrix and use a much smaller MZI mesh to represent a much larger weight matrix. And by doing this, you can actually reduce the number of MZIs and stages of MZIs by several times, and still allowing you to achieve pretty high accuracy for classification tasks. And when compared to other alternative technologies, analog and digital electronics, we've shown that we can then achieve a few orders of magnitude improvement in energy efficiency, again, both with digital electronic technologies and analog electronic technologies, and then also with other silicon photonic-based technologies, given the fact that we have these very low power phase shifters and non-volatile memory that we can use directly on the chip. So what's next, and how do we envision the future of computing within HPE and HPE labs? So these accelerators can be great for a specific kind of workload, but we're seeing that HPC systems and large-scale AI systems need to be able to handle a more diverse number of workloads. So no single accelerator, no single system can cost effectively satisfy all of these different workloads. So we need to design a platform to build heterogeneous computing systems that integrate various types of AI accelerator technologies together, including these photonic accelerators that I mentioned to you earlier. And that is kind of the future we see for supercomputing. And so if you imagine a system such as this, you'd see that these photonic accelerators can be just one of many diverse accelerators that can be used and integrated together within the system. And with photonics, we can also use these photonics for interconnects and networks that can be very high bandwidth and efficient. And what we imagine is that this would then be all kind of abstracted to, with compilers and then a software stack that allow users to then run all a diversity of different types of workloads and be able to efficiently run them, because depending on the type of workload, it would leverage that particular accelerator or resource that runs that workload most efficiently. So in 2008, we actually came up with this architecture in HP Labs called the Corona. I mean, some of you may remember this, but it was for heterogeneous multi-core architectures for processor units. And we used an optical crossbar to basically connect all of these different heterogeneous cores together. And it was kind of ahead of its time, being that this was, nearly 20 years ago. And we've actually started to look at developing or extending this work further towards now heterogeneous computing systems that have different computing nodes interconnected together. And you can build essentially all-to-all networks using a similar type of architecture. And so in this case, we're using photonic crossbars with microring resonators and TX and RX to be able to communicate from different types of processing units. And this provides you very low latency. It also provides you, it reduces the wiring complexity that would be needed to build an all-to-all network. With an all-to-all network with n number of nodes, you need n squared number of wires, and so that scales, and as you scale the size of your system quadratically, so you would reduce the number of wires. Doing that for that type of system could be just quite impractical, and so We've looked at these systems to lower the cost as well as the um, number of fiber count or cable count, as I mentioned. And we've integrated these photonic circuits or crossbars directly with electronic circuits for driving and for TIAs and amplification. And by doing this in 3D, we're able to, so we build TSVs directly on the photonic interposer and then put the CMOS integrated circuit directly sitting on top. And by doing that, then you remove the need for wire bonds, which helps in many different aspects. And going forward, we envision using these systems not just with one IC, of course, but with multiple ICs. So I'm just going to skip through a couple of slides here since I'm running out of time. So going forward, to build more extreme heterogeneous systems or heterogeneous computing that requires different types of accelerators for different workloads. We then envision looking at 2.5D and 3D integration to be able to integrate all of these accelerators together onto a photonic interposer, and that way it can be closely integrated with the photonics. And we've also built these memristive crossbars for very energy efficient accelerators for inference. And one project that we're actually involved in now is with the Microelectronics Commons in the Northwest AI Hub, where we're integrating these photonic interposers with resistive RAM-based analog electronic neural networks. And you get the best of both worlds. The photonics can provide you the massively parallel, high bandwidth networks and interconnects needed to connect these RAM chiplets together. And then, of course, the analog electronics can provide you the very low energy inference accelerator needed. And this is a part of a large collaborative effort with a number of teams from academia and industry. And yeah, we've also shown that you can get significant reduction in latency and energy consumption by moving to these silicon photonic-based interposers, and can be used for all-to-all networks directly for heterogeneously integrated chiplet systems. So just to conclude, shown that we've have built an energy-efficient, scalable 3.5 silicon photonic platform, which can be used for next generation interconnects as well as accelerators for next generation HPC. We've shown that we can demonstrate significant advantages both for I/O and for accelerators. And going forward, for the future of supercomputing, we imagine these more extremely heterogeneous computing systems, which require heterogeneous accelerators and ICs, and having photonics as the link between those accelerators that can be highly efficient and high bandwidth is the direction that we're also looking to as well. So thank you, and happy to answer any questions.
Thank you so much, Bassem, for your talk. We really appreciate it. If people would like to put questions in the chat or raise their hand, we can call on you. There already is one question from Elton, who I can actually take off of mute so he could ask his question directly, and maybe there's more since this came early in your talk. So hold on one second.
Hi. So yeah, I was asking earlier, do you guys well do the does the company, do you guys also use computing to like build like apps or train different like AI models?
Yes, yeah, we have several different groups, both within HPE labs and then of course within HPE, but within HPE labs, we also have those who are looking on the software side and looking and programming those accelerators for different types of workloads, scientific computing workloads and other AI type of applications. For us, we're kind of more focused on the hardware side of things, but there definitely across the company, across labs, there are people who are doing that.
Oh, okay, yeah, cause I have, I love AI so much, and so, I have this really cool idea, that'll be the next ChatGPT. So I was kind of curious, how do you guys work on stuff like that? So yeah, I was really wanted to learn more about that to see if I
Sure.
could how to, join you guys, team or group to see how that plays out. So yeah.
Sure. Feel free to, I have my email address shown here, so feel free to just send me an email and I'm happy to chat more offline.
Okay, let me take, yeah, all right.
Thanks, Elton. So we have an anonymous question. The person asked, I heard no details about the type of substrate. Was your work done on traditional ones, or did you use glass, diamond, or other substrates?
Yeah, we're just using silicon photonic substrates. So yeah, based on silicon. Uh, our platform, device platform is on there. We're able to then make the substrate actively reconfigured. The devices can be, you can have all types of devices directly on the substrate, right? So lasers, modulators, detectors, that we've all shown. So that's the main reason that we're sticking with that.
Great. Uh, we have another question from Falcon, who I'm going to allow to ask the question.
Sure.
Yeah, hi. Great talk. I was just curious, with regards to just foundries, are you using internal resources or you're a mix of what's available outside? If you can
Yeah,
say that, I don't mean to ask any proprietary question.
no problem. Yeah, that's a good question. So initially, we were pursuing this work kind of internally within our own clean room as well as a university clean room such as UC Santa Barbara and Anafab.
Mhm.
So we first developed our platform there, proof of concept, and then we started to transfer it to foundries. So right now we're kind of in that process of we're kind of partially doing both, where we use university clean room as well as foundry, but we're in the process of completely transferring over to foundry as well. So that should
Okay.
hopefully be available in the next couple of years.
Could I ask a quick architecture question?
Yes.
Um, what do you see as the key differences between what you're doing and, say, like some of the architectures that NVIDIA and Broadcom are following with the transceiver is very close to the chips, I guess, right? To kind of have the
Sure.
memory, being very close. Yeah.
Sure, that's a great question. So there's a couple of differences. First is the device platform itself. Device platform gives us the ability to scale these systems and make them very energy efficient. For example, the MOS capacitor-based modulators can be used for modulation as well as for phase shifters, and it can be done with very low power. Whereas I think what other people are looking into with current foundry access capabilities, they may be using other types of modulators or phase shifters that are not quite as efficient. So the device platform is one question or one answer to you. The second is the architecture side of things. Use this all-to-all network, which also is reconfigurable. So it's not just a passive all-to-all network that connects all of these different nodes together, but the fact that we can integrate our reconfigurable modulators and phase shifters. That reconfigurability allows you to also reprogram your network depending on the workload that you're running, and then that can actually mitigate traffic congestion in the network. So those are things that that's all being done in the photonic circuit itself, not on a separate electronic ASIC. Those are things that I think are a little bit more novel and maybe not yet what these other approaches are doing yet.
Thank you. We have Milan or Miloon. I'm sorry if I'm not pronouncing your name correctly, but they have a question as well, so I'm going to allow them to ask.
Sure.
Hello.
Hi.
Hey, my question is with respect to what sort of like out of all the technologies that are out there for optical compute, where do you see like the most likelihood of wide adoption or like replacement of GPUs in the next like 5 years?
Yeah, that's a great question. So I think in the next 5 years, it'll be pretty challenging for a photonic accelerator to replace a GPU, and I don't think that's the purpose in any case. Um, we see them more being complementary, and depending on the type of workload that you're running, you may use a photonic accelerator over a GPU, for example. I think that type of workload could be something like low processing, low latency applications. Some application examples could be edge computing or real-time processing, say for autonomous vehicles, for example, where you're processing raw data coming from sensors, and that needs to be done obviously in very high speed in order to prevent the car or vehicle from colliding with another. Um, and then having those kind of very low power accelerators directly in the vehicle rather than say a GPU, which can consume quite a bit of power. That's a direction I think that could be more feasible in the next 5 years. I don't think that at the current rate, photonic accelerators will again say replace GPUs in a data center just yet. But yeah,
We'll
that
still
that's
be purchasing NVIDIA stock.
sorry.
So we'll still be purchasing NVIDIA stock.
Yes, that's right. We'll still be purchasing NVIDIA stock for a long time, I think.
All right.
You're welcome.
So I'm going to take one more question because we're getting close to the hour mark. And this is from David Zhang. And David, I'm going to read your question out. Sorry, just due to the time limit we have. But his question is, how matured is I'm assuming it's AI or actually, I'm going to take David off of, because I want to make sure
No
that
worries.
the question is being asked correctly and I don't want to butcher it.
Sure.
Can you hear me? Hey, this
Yes.
is
Yes.
David. Yeah, yeah.
Sorry,
Sorry.
David, about that.
No, it's fine. I'll question quickly. So Benson, the very good talk. How matured is your all in all technology? As you said, you can have components all can all connect together, as you mentioned.
Mhm.
Scalability is a challenge. What is
Mhm.
the number of component size so far you guys have had in your design, and also what is the neural net if you use either spiking or just the conventional neural net? What is the size of the model you have achieved so far?
Yeah, no, that's a great question. So we've recently we demonstrated we haven't published this yet, but we've actually integrated a microring weight bank with photodetectors and an on-chip laser all together. And so, number of components there is like around, say, like 10, almost 10 components. Um, but again, they're all connected together directly on the same chip. So you're doing OEO, and we do see that cast or scalability wise, that tends to work pretty well. Just because those photodetectors are very robust. Doing something that's more like all optical, either for analog or for spiking neural networks, tends to be a little bit more finicky. But I think these components we can imagine and scaling, cascading many more of those components in the future. Um, I think, especially because you're regenerating your signal at each stage of the neural network when you go OEO.
I see.
So yeah,
Are you guys part of the Picasso program?
yeah, we have a team who's part of that.
Okay, good.
Yeah,
Thank you.
no problem. Thank you.
Thank you everyone for the great questions. And if you, sorry about that. If you have more questions, you can always email. Our next session or seminar rather is next Friday with Michael Gell from Sandia. So thank you, Bassam, for joining us, and we look
Thank you.
forward to seeing everyone. And have a great weekend. Thanks, everyone.
You too. Bye. Thank
Bye.
you.